We've completed a number of examples for the three-dimensional Schrödinger equation. Now we're going to stay in 3 dimensions, but we're going to talk about another operator in quantum mechanics called angular momentum. Now, classically, we think of angular momentum as our cross P, and the different components, Lx, Ly, and Lz, in the following way, just the outcomes of the cross products. In quantum mechanics, we treat angular momentum as an operator, and we're going to write it in these 3 following ways. So it's Lx hat is h bar over I times y partial with respect to z minus z partial with respect to y, and on and on. And those are the 3 components of the angular momentum operator when we talk about that in quantum mechanics. What we would like to do today is to deduce the eigenfunctions and eigenvalues associated with the angular momentum operator. Note, first thing you're going to notice is, of course, that they don't commute. In fact, we can write the commutators in the following way. Lx, Ly is equal to I h bar Lz. Ly, Lz is equal to I h bar Lx. And Lz, Lx is equal to I h bar Ly. Should look fairly familiar if we were using the spin operator. Those commutators look exactly the same, except s's instead of l's. There'll be more on that later. By the uncertainty principle, sigma Lx squared, sigma y Ly squared is going to be then greater than or equal to 1 over 2i h bar Lz squared, which is h bar squared over 4 times the expectation value of Lz squared. Another way of saying it then is uncertainty in x, uncertainty in y is greater than or equal to h bar over 2 times the expectation value of the z component of angular momentum. That tells us that we're not going to be able to find states that are simultaneous eigenfunctions of Lx and Ly, or Lx and Lz, or Lz and Lx. On the other hand, we can examine the total angular momentum squared. So if I square that operator, it's going to be defined as Lx squared plus Ly squared plus Lz squared. And we'll find that it does commute with each of the components of angular momentum. That is to say, L squared commutes with Lx, it commutes with Ly, and it commutes with Lz. We can show you, look, L squared, Lx commutator, I can write as Lx squared, Lx plus Ly squared, Lx plus Lz squared, Lz squared, Lx. And I can distribute that out. That will give me Ly, Lx plus Ly, Lx, Ly plus Lz, Lz, Lx plus Lz, Lx, Lz. Notice Lx, Lx, of course that commutes, so this term would be identically 0. I can write this then as Ly times IH bar LZ minus IH bar LZ Ly plus IH bar LZ Ly minus IH bar LZ Ly. Of course, I add these up. I got two pluses, two minuses. They cancel out. And so they commute. And of course, this would commute. Similarly, L squared would commute with L, Y, and LZ in the same fashion. And so we can write this in a shortcut fashion as L squared comma vector L is equal to 0. That means we can find simultaneous eigenvectors or eigenstates of L squared and Lx, or L squared and Ly, or L squared and Lz. So to do that, we're going to play with ladder operators again. Look for eigenstates of L squared and Lz such that L squared operating on some eigenfunction f gives me lambda f, and Lz operating on some eigenfunction f gives me some eigenvalue mu times f. So f is our eigenfunction in this case. And we're going to define two operators. We'll call it L plus and L minus. We'll just do them together. Lx plus or minus I Ly. Okay? Let's look at how or whether Lz commutes with L plus minus. So Lz L plus minus gives me the commutator that looks like Lz comma Lx plus or minus I times the commutator Lz comma Ly. And of course, we know that these two guys don't commute, and so it's going to be IH bar Ly plus or minus I times a minus IH bar Lx which of course is going to be equal to plus or minus H bar times Lx plus or minus I Ly. So that means that this commutator Lz comma L plus minus gives me plus or minus H bar L plus or minus. So, and along with this, of course, we know that L squared commutes with L plus minus, that's just 0, as well as commuting with Lx and Ly. That tells me that f is an eigenfunction of both L squared and Lz, and therefore so is L plus minus f. Do I know that? Let's see. L squared applied to L plus minus f gives me L plus minus L squared f, which is equal to L plus minus lambda times f, which is equal to lambda times L plus minus f. Now, Lz applied to L plus minus F gives me LZ, L plus minus L plus minus LZ, applied to F plus L plus minus LZ F. If I work out those commutators, that's going to give me plus or minus H bar L plus minus F plus L plus minus mu F. Or it's equal to mu plus or minus H bar times lambda plus minus F. So lambda plus minus F is an eigenfunction of LZ with some new eigenvalue, mu plus or minus H bar. In that sense, we can look at L plus as a raising operator. Raise is the eigenvalue from mu to mu plus H bar. L minus then, of course, is a lowering operator because it raises the eigenvalue from mu to mu minus H bar. Very interesting. Kind of reminds us of that algebra method with the harmonic oscillator. So for a given lambda, we get a ladder of states. Each rung of the ladder is separated by H bar in the eigenvalue LZ. So to go up, I apply L plus. To go down, I apply L minus. Okay, very interesting. What else do we get from this? If I keep going up the ladder, and I keep applying L plus, all of a sudden, LZ will be greater than L squared. And that can't happen. We can't allow that. That's not physical. So what we have to do is we assume that in our ladder there's a top rung. I can't go any higher than this. And I'm going to say that that rung corresponds to a state F sub t for top, such that when I apply my raising operator L plus to that top, better make that more clear, it's not a plus, it's a t for top, I get 0. That's the end of the ladder. I've reached the maximum height, so to speak. So suppose H bar L is the eigenvalue of LZ at the top rung, which means H bar L times F top is equal to LZ times F top, or applied to F top. Moreover, L squared applied to F top would be equal to the eigenvalue lambda F top. Interesting, interesting. Let's play with this just a little bit. Suppose I take L plus minus, L minus plus, and write that as Lx plus or minus ILy, Lx minus or plus ILy. And if I multiply that out, I'm going to get Lx squared plus Ly squared. And it's going to be minus or plus I times Lx Ly minus Ly Lx. Which I can write very conveniently as L squared minus Lz squared plus or minus I times I H bar Lz. Another way of saying this is L squared then is equal to L plus minus L minus plus Lz squared minus or plus H bar Lz, right? I times I is I squared. Minus goes to a plus goes to a minus. Now suppose I apply this operator to my top rung eigenfunction. So if I apply L squared to ft, that's like applying all of these guys. So I'm going to apply this to ft, I'm going to apply this to ft, and I'm going to apply this to ft, and then I'm going to apply this to ft. What do I get? This will give me, this is going to give me first 0. Second term will give me plus h bar squared L squared plus h bar squared capital L, all applied to ft. Put it all together, what do I get? H bar squared L plus 1 times f sub t. That means lambda, my eigenvalue for L squared, lambda would be equal to h bar squared times L plus 1. This is the eigenvalue of the maximum eigenfunction for Lz. This is pretty suggestive. Let me just stop right here and say, this L times L plus 1 reminds me of this, of the constant that we used when we were looking at the solving the Schrodinger equation and separating variables. Maybe we knew what we were doing back then. Okay, but now let's do the following. Let's take it from the other direction. There should be a bottom rung of the ladder, just as there is a top rung. We'll call that the eigenfunction at the bottom of the rung f sub b, such that when I apply this minus, this lowering operator to it, I'm going to get 0 as well. I can't go any lower than this. And we're going to let h bar L bar be the eigenvalue of Lz. So what that means is if I apply if I apply Lz to f sub b, I will get h bar L times f sub b. Moreover, if I apply L squared to f sub b, I'll get, again, lambda f sub b. So let's apply L squared to f sub b, which I'm going to write as L plus L minus plus Lz squared minus h bar Lz applied to f sub b. Just similar to what I did before. I'm going to get 0. I'm going to get plus h bar squared L bar squared minus h bar squared L bar f sub b, which I can write as h bar squared L bar minus 1 f sub b. Therefore, in this case, lambda, my eigenvalue at the lowest rung, lambda is going to be equal to h bar squared L times L bar times L bar minus 1. Well, from this, looking at the other side, we can conclude that L bar is none other than minus L. Great. What about the eigenvalues of L sub z? Let's look at that. The eigenvalues of L sub z, so L sub z times f top will be equal to h bar L f top, top rung, Lz applied to f bottom is h bar times L bar times f bottom, the bottom rung. So in general, the eigenvalues of LZ will just be some integer times h bar. We'll call that integer m, and m ranges from minus L to plus L in integer steps. That means, let's say I have n integers between minus L and plus L. That means L is equal to minus L plus n. Therefore, L is equal to n over 2. So L is either integral or half integral. That's interesting. We're going to use L and M to characterize our eigenfunctions. In other words, L squared, my angular momentum operator squared, applied to this eigenfunction FLM is going to be equal to h bar squared L plus 1 F sub Lm. And LZ applied to FLM is going to be equal to M h bar F sub L. And in this case, L can be equal to 0, 1/2, 1, 3/2, etc. M ranges from minus L plus 1 on up to L minus 1 and L. So for a given value of L, there are 2 L plus 1 values of M. So by raising and lowering algebras, we've calculated the eigenvalues for L squared and LZ without actually determining their eigenfunctions. Having done what we did with the angular part of the Schrödinger equation for the hydrogen atom, for example, well, in general, right? Any radially, any potential that depends upon only the radial coordinate. Angular dependence, we expect fully that these eigenfunctions should look like the spherical harmonics when we get there. Hopefully that will be true. Next time we're going to write the eigenfunctions for angular momentum and indeed show that those eigenfunctions are the spherical harmonics.